Professor Zioma Donwekpete, welcome my viewers and students to another interesting lecture on the group 14 elements, also known as the carbon family. Don't forget to subscribe, like, comment, and share this video. Thank you for always viewing my channel. The objective of this lesson: by the end of this lesson, the student should be able to identify the elements in the group 14 of the periodic table, write their electronic configuration, describe their periodic trends, and write the equation of the formation of their oxides and halides, and also describe the oxidation states of the group 14 elements. The group 14 elements or group 4A elements contain two of the most important elements on Earth: carbon, the fundamental constituents of the molecules necessary for life, and silicon, which forms the basis for geological world. We have the elements as carbon, silicon, germanium, tin, and lead. Carbon has an atomic number of 6 and a valence shell of 2s2 2p2. Silicon has atomic number 14 and valence shell 3s2 3p2. Germanium has atomic number 32 with valence shell of 4s2 4p2. Tin has atomic number 50 with valence shell 5s2 5p2, and lead with atomic number 82 with valence shell 6s2 6p2. Table 2. Selected physical properties, sources, and methods of preparation of 14 metals. These elements, carbon, silicon, germanium, tin, and lead, are the elements of group 14. And it is observed that metallic tendency increases down the group, carbon being non-metal and tin and lead being metals. We observe also that electronegativity decreases down the group, with carbon having the highest electronegativity of 2.5. Melting point also decreases down the group, with carbon having the highest, and it sublimes at that 3727 degrees centigrade. Boiling point decreases also down the group. The sources of carbon are graphite, diamond, petroleum coal, and maybe fullerenes and carbon nanotubes, etc. The silicates minerals are sources of silicon, and silicon can also be gotten from silica. Germanium can be gotten from germanite, which is a mixture of copper, iron, and germanium sulfide. And tin can be gotten from tin dioxide, called cassiterite, while lead can be obtained from lead sulfide, known as galena. What are the methods of preparation of the elements of this group? Carbon can be obtained from nuclear fusion in bigger stars. It is present as carbon dioxide in the atmosphere and is found in fossilized remains as natural crude oil or coal, etc. And silicon can be obtained by the reduction of potassium hexafluorosilicate with aluminium, or reduction of silicon dioxide with magnesium, while germanium can be obtained from the reduction of germanium dioxide with hydrogen or carbon. Tin can be gotten from the reduction of tin dioxide with carbon, and lead by the reduction of lead sulfide with oxygen to form lead dioxide, and then reduction with carbon. Properties continues. The atomic radii of these elements of this group increases down the group, primarily due to the addition of new energy shell at each succeeding element, and we found that there is an increase in atomic radii from silicon And that one down to lead, is not so high. Maybe due to the elements are now having filled or completely filled D and F orbitals. We also observe that ionization energy decreases down the group, with carbon having the highest ionization energy, and ionic radius increases down the group, while electron affinity decreases down the group. How are these reactions of these elements? Elements of this group react with oxygen. For carbon, it forms carbon monoxide and carbon dioxide. So all members, when heated in oxygen, form oxides, and they can form MO or MO2 respectively, as seen from the table. And then there are oxides. For carbon oxides, carbon dioxide is acidic, while carbon monoxide is neutral. Silicon dioxide is weakly acidic. Germanium dioxide is amphoteric. Tin dioxide is amphoteric, and lead oxide is amphoteric. Reaction with nitrogen is silicon and tin that reacts with nitrogen. And reaction with halide, all elements of this group can form halides of formula MS2 and MS4. And we know that S represents fluorine, chlorine, bromine, iodine. That is the members of the group, 7 elements of group 17. Heavier elements like germanium and lead are able to form dihalides. They're able to form their dihalides as MS. That is the heavy elements. And the stability of dihalides increases down the group, considering thermal and chemical stability. GeS4 is more stable than GeS2, whereas lead S2 is more stable than lead S4. And what of the reaction with hydrogen? It is only carbon that can react with hydrogen to form hydrocarbons. Others don't react with hydrogen. There are oxidation states. The group 14 elements have 4 electrons in their outermost shell. All the elements show an oxidation state of +4. However, methane is not an example of that, because methane shows an example of a -4 oxidation state, because carbon is more electronegative than hydrogen. And also, it can exist as +2, like in lead ion, in lead oxide, and in tin dichloride, as shown on the slides. So moving down the group, there are more examples of +2 oxidation states, due to the increase in Napier effect. Formation of bonds. For the group 14 elements, we all know that they have 4 electrons in their outermost shell, and therefore they require 4 more electrons to reach an octet. These 4 electrons can be gained by forming covalent bonds, as illustrated in methane, in carbon tetrachloride, in silicon, in silane, SiH4. We use the example of carbon here. Carbon is a non-metal in that group, and we know that it has 4 valence electrons. The valence electron of 4, that means it requires 4 other electrons to form this complete octet. So carbon can react with 4 hydrogen to share bond, forming a covalent bond. can bond with 4 hydrogen atoms. The electron dot diagram shows the shared electrons, and the structural formula is represented with a dash. That dash represents the bond between carbon and hydrogen. And carbon can form single bonds, double bond, and triple bonds, as shown in ethane, and in ethine. In ethane, it forms single bonds, C2H6. In ethene, it forms double bond, C2H4, and in ethine, it forms a triple bond, C2H2. Some allotropes of carbon. And allotropes are elements that can exist in 2 or more forms with differences in their physical properties. And carbon is an example of allotropes, or an element that can exist in more than one form. Carbon can exist as graphite, as diamond, as fullerenes, and recently as carbon nanotubes. As graphite, graphite occurs naturally and is the most stable form of carbon under standard conditions. Graphite is much in abundance in China, India, Brazil, North Korea, and Canada. Graphite is useful in pencil making, as lubricant, in crucible, and foundry facing. Graphites are very useful as cores of nuclear reactors. Another allotrope of carbon is diamond. Diamond is a mineral composed of pure carbon. It is the hardest naturally occurring substance known. It is also the most popular gemstone, very useful in industrial applications. And diamond is very useful and in abundance in Australia, Botswana, Brazil, China, Congo, Russia, and South Africa. We find out here that diamond is very common in some African countries. They are useful as drilling bits in oil exploration and for slicing through concrete, because it is said that it is the hardest naturally occurring substance known, and for jewelry. Jewelries made of diamond are very expensive. Another allotrope of carbon is the fullerenes. The fullerenes. Fullerene is an allotrope of carbon whose molecule consists of carbon atoms connected by single and double bonds with fixed 5 to 7 atom rings. And the first fullerene was comprising of 60 carbon atoms, was discovered in 1985 by Sir Harold Kroto, Richard Ehret Samley, and Robert Ford Cole Jr. Fullerenes are useful as conductors, as absorbents for gases, as lubricants, in making cosmetic-related materials, and very useful in biomedical application. A most recent allotrope of carbon is carbon nanotubes, discovered in 1991 by Simo Ijama, a Japanese physicist. It is very useful as automatic parts, boat hose, water filters, thin film electronics, and electronic shields. These allotropes are useful to mankind. Some uses of group 14 elements and compounds. Activated carbon, also from carbon, are used as air filters, gas masks, aquarium water filters, and water purification plants. Also, activated carbon can also be taken in and used as an odor remover, and it kills bacteria in the stomach. Those are proven uses of activated carbon. Silicones are used as waterproof fabric because their oxygen atom attached to the fabric, leaving the hydrophilic metal groups like tiny inside-out umbrellas sticking out of the fabric surface. Lead is durable and malleable, which makes it useful in the construction industry. Lead is very dense, which makes it ideal as radiation shields for X-rays. And also, lead is also used as electrode for rechargeable batteries. And tin, which main use is in tin plating and used in alloys such as bronze. Germanium is used in the semiconductor industry. Thank you as we have come to the end of this lesson. But we'll have some study questions to attempt. Questions 1 to 3 says predict the products of the reactions and write a balanced chemical equation for each reaction. Question 1. Let dioxide solid decompose in what are the products of the reaction? 2. Germanium tetrachloride solid plus water liquid give the product of the reaction. And then the third one says lead solid plus chlorine gas give the product of the reaction. Question 4 says, what is the oxidation state of carbon in the following compound? CH4, methane, and then in carbon tetrachloride, CCl4. Then 5 says, list 3 allotropes of carbon and 3 of their uses. Thank you. We have come to the end of this lesson. We have also come to the end of this year. Don't fail to subscribe, like, comment, and share this video. Wishing everyone a blessed 2024. See you in the next class.